we have reached the halfway point in our journey through algebraic functions. So we've looked at the straight line, y equals mx plus c, the parabola, y equals ax squared plus bx plus c. Remember, anything with the squared makes me think of these quadratic functions. And we learned two different variations of that, so the turning point form and the x-intercept form. And now in this video, we move on to the hyperbola, which is a very interesting graph that actually, once you know the foundations of it, it's quite straightforward. So the equation of the hyperbola, y equals a over x plus p plus q, and these values here link to what is known as asymptotes. So let's dive in and see exactly what the hyperbola has in store for us. The first thing that we look at is the standard form. So this equation here tells us a lot about a hyperbola. The first thing we do is we say, okay, what is the a value? That tells us the shape of a hyperbola. So if a is positive, then our hyperbola occurs in quadrants 1 and 3. And if a is negative, it occurs in quadrants 2 and 4. Okay, so how do we write that? We say a is positive, greater than 0, or a is negative, smaller than 0. And then the other thing that our standard form tells us is that there are asymptotes involved. Okay, so an asymptote, I always like to picture it as a type of electric fence on a graph. You can get very, very close, but you can never touch it and you can't cross it. And so there are two of those in the hyperbola. Okay, we can also work out intercepts. And so this should become second knowledge to us by now. To get a y-intercept, we let x equal 0. And to get an x-intercept, we let y equal 0. Okay, now we're ready to look at those things called asymptotes. So on our graph, we will have two lines that this hyperbola cannot touch. Okay, the one line is that linked to the p-value there, okay? And remember that we always change the sign. So that's our first asymptote, okay? When it comes to the x value, we use the opposite sign, so the asymptote is x is equal to minus p. And then the other asymptote there linked to the q value, that one is straightforward, y is equal to q. So on every hyperbola, we've got two asymptotes. If it's not specifically stated, then you need to remember that that's probably the number 0, which means one of the axes then becomes an asymptote. Okay, but we've got two asymptotes that we need to know. There's an x one where we change the sign of the p coordinate, and there's a y one where we keep the sign of the q coordinate. Okay, or q value in the graph at least. And those two asymptotes help us then to figure out how to draw our graph. So let's say you have a positive a value and you've got these asymptotes in place, then your graph will occur here and here. And so you'll see you'll have a y-intercept and an x-intercept when you draw it. Okay, domain, those are the x values for which a graph like this can occur. Okay, so the minute that I see something in a denominator, I'm already thinking, ooh, there could be some undefined values here. And then it makes perfect sense that we actually have an asymptote here in place. So we can draw a hyperbola for any value of x except for that asymptote value. So you can say x is an element of the real numbers, but x is not allowed to equal whatever the asymptote value is there. Okay, so that's that value. And then the same is true for y. So y can be drawn anywhere here, anywhere there, but it's never allowed to cross or equal that q value. So we can say y is an element of the real numbers, but y is never allowed to equal whatever that asymptote value is. Now let's consider the axes of symmetry. Okay, so an axis of symmetry is a line that we can fold our graph on so that the two halves are perfect mirror images of one another. And the hyperbola has got two of those. So let's picture a hyperbola that's just got asymptotes here on the axis, on the x and y axis. And we can quickly draw in some arms here. There's one, and there's 1. Okay, we're obviously going to shift this thing around quite a bit as we move along. But for now, just to get this concept down of an axis of symmetry, there are 2 lines. There's one here that gets drawn, and that has a standard form, y equals x plus c. And then there's another one that gets drawn with a negative gradient. So over here, and that is equal to y equals minus x plus c. And then the only thing that you need to remember is to substitute in. So you start with these foundational formulae, y equals x plus c, y equals minus x plus c, and then you sub in the intersection of the asymptotes, or a point of intersection of the asymptotes. And that will help you to calculate the axes of symmetry in this instance. Okay, so that means we've got a point here, minus P and Q, that we would sub in. Okay, now at the moment it all looks like so much theory, but once we jump into some practical examples, I think you'll see it actually is quite practical and very much something that you'll be able to do. Okay, here we go. Sketch the graph of f of x is equal to minus 1 over x minus 2 minus 1. All right, so what we want to do is we want to just go through our steps that we normally do. Okay, so I start and I say, right, what is the shape of this graph? And shape comes specifically from that value there, and that tells us it's got a negative shape, which means it's going to be in quadrants 2 and 4, because a is a negative number. Then I like to get the asymptotes in place. So asymptotes, where do they come from? Those are the 2 values there, those linked to asymptotes. Okay, so remember our x asymptote is actually the minus p value. So x is equal to minus 2, which is positive 2, and then y is equal to negative 1. Then we can work out some intercepts. So an x-intercept, we let y equal 0. Okay, so let's do that. We've got 0 equals minus 1 over x minus 2 minus 1. Let's move this minus 1 across. It's going to become plus 1. I'm going to put it over 1 because we're going to need to cross multiply now. Okay, then I'm going to say the top of this fraction multiplied by the denominator here, and the denominator of this fraction multiplied by the numerator here helps me to cross multiply. Okay, it's like a shortcut for getting a common denominator. So 1 times x minus 2 is equal to 1 times minus 1. And then if we move that minus 2 across, we'll see, oh, x is actually just equal to minus 1 plus 2, which is 1. Okay, we've got an x-intercept. Now, to get a y-intercept, we let x equal 0. All right. And then what we do is we can sub straight in. So y is equal to minus 1 over 0 minus 2 minus 1. And if we calculate that, we end up with minus 1 over minus 2, which is just a half. And a half minus 1 is minus a half. Okay, and once I've got all of these things in place, I am ready to start sketching. Okay, I'm going to label my axes. So I can see here I need lots of 1s and 2s, and I've got a half there. So let's go up in 1s. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, etc. Remember, you get marks for labeling all your intercepts. So if you label your axes, you are ensuring that you are going to get those intercept marks that you need. Okay, now what I like to draw next is the asymptotes. So let's get those in place. It's very important that you label them. So y equals minus 1, x equals 2. Now we can draw in our intercepts. So we've got an x-intercept there of 1. Let's pop that on the x-axis. And a y-intercept of minus a half. So that's down there. Okay, and then we know that it needs to be in this region and in this region here. Okay, I'm ready to draw in quadrant 2. If you have a look at that, I've got 2 points. And we need to have 2 points to be able to draw something accurately. And so there we go. That's the one arm. But what you'll notice here is that we don't have any information for this section of the graph. And that is not a problem, because we've got this whole equation here that we can actually work with. So let's substitute in some values here just to see what we should be plotting. So it's almost like we're going to just table method this part of the calculation so that we can draw the rest of our graph. Okay, so we're going to say, what is f of 3? Because that's one of the values there. Okay, so let's calculate that over here. And so everywhere I see an x, I'm going to substitute in a 3. Minus 1 over 3 minus 2 minus 1. Okay, let's see, minus 1 over 1 minus 1. That gives us a minus 2. So now I can plot when x is equal to 3, y is equal to minus 2. And that makes sense in that region. Okay, there's 1 point. And then let's do the same with the point 5. So let's work out f of 5. So now we're going to say minus 1 over 5 minus 2 minus 1. And let's see what we end up with there. 5 minus 2 is 3. So we've got minus a third minus another 1. So it's minus 1 and a third there. So 5 and minus 1 and a third. Probably going to be around about there. Okay, so once you've calculated all of these, you may find, just like we've done now, we had 2 points in one of the quadrants. And so then we needed to do a couple more calculations just to be sure that we could draw this graph as accurately as possible. And then once we've drawn it, remember to name it. Okay, sometimes they give us a graph like this and they say determine the equation of the function below. So the first thing that I like to do is I like to say, what type of function am I looking at? And this one is easy because we were in a video on hyperbolas, but if it was a mixed example, that would be my first steps. Just to say this is hyperbola, and then we write down the standard form. So the standard form is y equals a over x plus p plus q. Okay, and once I've done that, I then say, all right, well, what do these things refer to? P and q and a. A tells me the shape. Have a look at this. This is in quadrant 1 and 3, so it's going to be a positive a value, whatever it ends up being. And then P and Q are linked to these asymptotes. So they've given me the coordinate here of the intersection, which helps me actually, because I can decipher that and I can say the x coordinate is 2, meaning that the x asymptote here is x equals 2. And the y coordinate is 3, meaning that the y asymptote is 3. So that's what those dotted lines are representing. So I can pop that into my equation, but remember that x is equal to minus p and y is equal to q. So when I sub that in there, I just need to make sure, okay, that means p, if I don't want the minus there, is equal to minus x. So in other words, I'm going to sub in a minus 2 and a positive 3. So that's going to be my next step. Sub in the asymptotes. Okay, so y, I'm subbing in for p and q. This is where people sometimes get confused. They instead sub in for x and y, and that doesn't work out very well for them. Okay, so y is equal to a over x minus 2, look at that sign change, plus 3. And once we've done that, we sub in one other point. Okay, so I've used the asymptotes, and this point is not on this function. So we can't sub in 2 and 3. We've used it now for what it stands for. I now need to go and look at this point here. This is an x-intercept. So for an x-intercept, y is equal to 0. So that means the coordinates there are actually 1 and 0. So that's what I'm going to sub in. In the place of y, a 0. In the place of x, a 1. Now let's solve. We've got a over minus 1 plus 3. And then let's multiply everything then by minus 1. 0 times minus 1 is just 0. A over minus 1, that's just going to go away. And 3 times minus 1 is minus 3. And then if we take that across, a is equal to 3. And so then therefore, our equation is y is equal to 3. It's positive, just like we had hoped, over x minus 2 plus 3. Okay, so that's how we determine the equation, is then we sub back in to step 1. So we'll take that answer there, and we want to put it all the way into the a value up there.